Hello everyone, let's continue the reactions of aromatic molecules. This is a reaction we discussed in the previous discussion. The elimination addition reactions of aromatic molecules. Again, this is a nucleophilic substitution reaction. This is just one of the mechanism of the nucleophilic substitution reaction. In the nucleophilic substitution reaction, one of the key points is the strong nucleophile or strong base. In this reaction, we use a very strong base, sodium amide. So if you check the pKa values from chapter 1, you can see this is this is sodium amide is very strong. Actually, the first step reaction is an elimination reaction because there is a chlorine here is very good leaving group. So the first step is the elimination of hydrogen HCl. Again, because of the basicity of the sodium amide is so strong, we do elimination reaction to form alkanes. The next step is the amide, the strong base, attack either this carbon or this carbon. So whenever the amide attack this carbon, we are going to form this addition product. So the similar mechanism here. This is the addition product. This addition product, they are also very strong base because they still have a lone pair of electrons, not a lone pair of electrons, but also a negative charge. So they are still very strong base. So they are going to react with ammonia here. So one of the ammonia molecules is going to provide a protein which serves the acid to do the protonation of this anion and this anion to form the final product. So this is the final elimination addition react. This is also a nucleophilic substitution reaction. So the result is chlorine is replaced by the amine group because of the intermediate is alkyne, the carbon-carbon triple bond. So the substitution product, the substituent could be at the chlorine carbon's neighboring carbon, which means either this carbon or this carbon, but never at this carbon or this carbon. Let's continue the reactions of aromatic molecules. The next one is the bromination or halogenation of alkyl benzene. Alkyl benzene means you have a benzene ring, you have an alkyl side chain of attached to this benzene ring. We can do radical reactions with this type of aromatic molecule. This is aromatic molecule, or this part is alkyl molecules. So actually, if we do a radical reaction, we are going to halogenate the alkyl part, but not the benzene part. Again, the conditions for radical reactions, either whenever you see a light, we use H-mu, which means light. I would like to say it's UV light. It has to be a very high energy light. Heat condition, or we use the peroxy molecules. So you see one group here, one group of 2 oxygen. This is called a peroxy molecule. Peroxy molecule, normally a radical supplier. So whenever we see this molecule, think about radical reaction. NBS, the structure of NBS. So whenever you say NBS, you don't have to draw the exact structure of NBS, but I want you to remember NBS basically is a very low concentration of bromine. So this condition, basically they are equal. So when we do the radical bromination reactions of benzene, alkyl, actually the radical reaction will attack this carbon here to form a radical. This is the structure. Radical attack this hydrogen, and one electron is here. Another electron goes to hydrogen, and hydrogen and a radical forms something else. Yes, hydrogen added radical here. So, well, if we draw the resonance structure, we can draw so many resonance structures. That's why the radical prefer to attack this bond to form two radicals, radical 1, radical 2. So because this reaction is much easier than the radical to attack the benzene ring. That's why we have the halogenation reaction actually on the alkyl side, but never attack the benzene ring. And let's compare the bromination of alkyl benzenes. Again, this is the reaction we just discussed. This is a radical mechanism. We have a bromine. We do bromination of this benzene, alkyl, or alkyl benzene. The reaction will always enter the first carbon connected to the benzene ring. However, this is the reaction we learned in the first lecture of this chapter. If we used iron bromide as the catalyst, this is an electrophilic substitution reaction. Actually, either this hydrogen, that is the ortho hydrogen relative to this alkyl group, or at this position, it is the para position relative to this alkyl group, and we know this alkyl group is the ortho para director. So the reaction will never happen here, will never happen here, because this position is the met position relative to this ethanol group here. So again, this is an electrophilic substitution reaction. The key point for electrophilic substitution reaction is how we generate an electrophile. An electrophile basically is something, a molecule that bears a positive charge. So the catalyst iron bromide here actually help us to generate an electrophile, that is molecule bearing some positive charge. Then the electrophile is going to attack this benzene ring to form either ortho isomer or para isomer. Again, the details of this ionic reaction or radical, this is not radical, this is the electrophilic substitution reaction. It's covered in the first chapter of in the first lecture of this chapter. Again, NBS in your mind is a bromine. The next reaction we are going to discuss is the oxidation reactions of alkyl benzene. This is a pretty simple reaction. We are not going to discuss the details of the mechanism of this reaction. You just need to remember this reaction, and again, it's very simple. So if we have a benzene ring, we have an alkyl. Alkyl, this could be CH3, could be CH, CH2, CH3 here, CH3 here. Alkyl group means this carbon is sp3 carbon. If you have an sp3 carbon attached to a benzene, this is alkyl benzene. So regardless of the variation of this alkyl group, could be just a simple methyl, could be isopropyl, or could be ethyl, like in this case ethyl, actually two ethyl groups here. The oxidation reaction always carboxylic acid, benzoic acid, or we simply say benzoic acid. Benzene ring and a carboxylic acid. Regardless, again, the variation of the structure, always benzoic acid. If you have two alkyl ring, you are going to form two acid groups here. The only the oxidative reagent is a very strong oxidative reagent here. The only requirement is this carbon, the first carbon which connected to the benzyl ring, this carbon has to have at least one hydrogen here. Like in this case, this carbon has 3 hydrogen, CH3. This carbon has 1 hydrogen, CH here. This one has 2 hydrogen, CH2. This one, this carbon, it is an sp3 carbon. So, but there is no hydrogen at all. This carbon attached to CH3 here, CH3 here, CH3, and a carbon in the benzene ring. There is no hydrogen at all. Actually, there are 2 requirements for this oxidation reaction. First, you have to have very strong oxidative reagent. Second, you have to have that carbon hydrogen bond here. If you have a carbon hydrogen bond plus a strong oxidative reagent, you form benzoic acid. So you could have one or you could have more. If you have a third CH3 here, you will have a third carboxylic acid group. Again, this reaction is pretty simple. We are not going to discuss the mechanism. So the next reactions we are going to discuss is the reductions for different aromatic molecules. Like this one is called acyl. So this part is acyl. This part is acyl. So we can reduce the ketone groups here. Well, the ketone is the alkyl-CH3 and benzene here. This ketone can be reduced by zinc, mercury, alloy plus the HCl, strong acid condition, in strong acid condition at a relatively high temperature. Basically, this both carbon oxygen bond are replaced by carbon hydrogen bond. You know, that's a reduction reaction. That's the definition. Carbon oxygen replaced by carbon hydrogen. That's reduction reaction. And there is a name. It's called a Clemmensen reduction. Very likely Clemmensen is the chemist who discovered this reaction. Again, ketone molecule can be reduced by zinc, mercury alloy, and acid condition. The next condition, you know, sometimes if we cannot do a reaction in strong acid addition, we have to do the reaction in base condition. And the good news is another chemist, Wolf Kirchner, very likely these are 2 chemists who discovered this reaction. In base condition, if we use another reducing agent here, we can reduce hydrogen. This is hydrogen. Hydrogen is a very strong reducing agent. So in this case, actually, it's hydrogen. You see, if you have zinc, you have HCl, basically you generate hydrogen. The real reducing agent here is hydrogen gas. In this case, the reducing agent here is hydrogen. Hydrogen reduces the carbon-oxygen bond into carbon-hydrogen bond. That's another reduction reactions of aromatic molecules. Alright, so 2 reduction reactions of ketones, either an acid condition or base condition. Let's take a look at more reduction reactions. So nitrobenzene, nitro group can be reduced to amine groups. Again, this reaction basically is the reduction of a nitrogen-oxygen bond into a nitrogen-hydrogen bond. That's a typical reduction reaction. We can use the hydrogen gas as the reducing agent with the palladium supported on charcoal. This is a catalyst. So hydrogen gas is a very strong reducing agent, which is able to reduce the nitrogen-oxygen bond into a nitrogen-hydrogen bond. Other conditions like iron plus HCl, basically the iron plus the strong acid HCl that you are going to generate hydrogen. So hydrogen serves as a strong reducing agent on different metals like tin. So this is a reduction reaction, and nitro groups can be reduced to amine groups. So this reaction, this is interesting. This is a nitro group we have, but this is not ketone. This is ester. So nitro group can be selectively reduced to amine group, but this ester group will not do the reducing reaction. So please keep in mind, this is ester carbon, oxygen double bond, then another oxygen here is ester will not be reduced. But a ketone, see, the structure in the previous slide is ketone, not ester. It's pure carbon oxygen bond. Carbon oxygen double bond can be reduced here, but a carbon oxygen plus another oxygen ester group is not reducible with the hydrogen. All right, now let's take a look, some synthetic skills or synthetic tricks to do organic molecules synthesis. So, for example, if we want to make this molecule, this is our target molecule. Benzene ring attached to the propyl, 3 carbons, alkyl chain here. How we make this molecule from benzene? Very simple way to do this reaction is the Friedel-Crafts reaction. We can react with the benzene with the alkyl propyl chloride, alkyl halide, the catalyst to do the Friedel-Crafts reaction. This is a Friedel-Crafts reaction, which basically introduced the alkyl group into the benzene group. Unfortunately, so this would be the final product. You're not going to get this product because the carbon cations, the rearrangement reaction. We discussed the details in the first lecture of this chapter. If you don't fully understand why the structure changes 3 carbons in one chain, but now at this moment 3 carbons still in the chain, but the reactive part not under the end carbon here, but the middle carbon is because of the rearrangement of the carbon cation. So this would not be the product, but this rearranged the product. Well, if you are a good organic chemist, so this is probably the way to make the target compound. So you have to do multiple step reaction. First step to do the acylation reaction. So basically acid chloride react with benzene. This is the second type of a Friedel-Crafts reaction. Called Friedel-Crafts acylation reaction, and the same catalyst, aluminum chloride. So good news for this type of Friedel-Crafts acylation reaction, there is no carbon cations rearrangement. So the reaction product is very straightforward and very clear. Basically, the bond will be connected here to the ketone groups. So this would be the product. But this is not our final product, and we don't mind to do one more step, to reduce this carbon oxygen ketone group, carbon oxygen double bond into carbon hydrogen bond. This is a reduction reaction. Again, this is we can use zinc, mercury alloy, and a strong acid condition. And basically, this is hydrogen. Reduce the ketone group into a CH2 group here. Very typical reduction reaction for aromatic ketones. All right, one more examples we want to practice here. Again, this is the target molecule. This is the molecule we want to synthesis, and I want to think about the way to make this molecules with all the reactions we learned in the whole chapter from lecture 1 till today. Well, this is benzyl. This is a benzyl aromatic molecules. The starting molecule very likely is a benzene, so we can use benzene to make this molecule. Let's just take a look of the two functional groups. One is nitro, the second one is acid group here. Well, for this type of reaction, I talked before, we want to think about it both ways. First, we have a benzene. That's what we have in our lab. So from benzene, what else we can make? We have to list, all organic molecules we can make from benzene. So this is one way to do this type of synthetic work. Second way is, look at the target molecule. This is molecule I want to make. What kind of molecule I need? The immediate predecessor here I need to make this molecule. This is a till both ways meet each other. Well, if we have benzene, we need a nitro group. We can do like electrophilic substitution reaction to do the nitration. Electrophilic substitution reaction. That's the reaction we learned from the first lecture. The acid group. The only reaction we learned in this chapter to do the benzoic acid here is probably what we just discussed, the oxidation reaction. Let me show you. See, oxidation reaction, we have to introduce an alkyl group first, then do oxidation reaction, then we are going to have the carboxylic acid group. All right, so that's basically the thinking process. We need to introduce like a methyl group here, introduce a nitro group here. So now the next question is to introduce methyl group here first, and introduce the nitro group here first. We know methyl is also parity reactor. If we introduce methyl group here, then do the nitration reaction, we will have nitro group either here or here. That's not bad. However, let's take a look. If we introduce the nitro group first from benzene, forget about this part first. If we introduce the first part here, nitro group, do the nitration reaction from benzene to nitrobenzene here, then the question is how we introduce the methyl group here. So we know to introduce the methyl, the alkyl group, to a benzene ring, the typical reaction is a Friedel-Crafts alkyl reaction. But whenever we introduce this nitro group, it is a very, very strong electron withdrawing group. So if you have a very strong electron withdrawing group, you are not able to do the Friedel-Crafts alkyl reaction because the electron density in this benzene ring significantly reduced by this strong electron withdrawing group. So that's not a good way. By analyzing the two possible role to make this molecule. I think the first one, introduce that methyl group right here first, then introduce the nitro group here, then do the oxidation reaction. You know, that's basically that's basically the thought process. You know, benzene to do the Kraft alkylation reaction, you introduce the methyl group here. The next one to do the nitration reaction. So again, this is the para position relative to this methyl group. This is a not bad reaction. Then oxidation of this methyl group to generate this carboxylic acid group. So here, this is a whole process in making the molecule. All right. I think I made a mistake here. The structure is not correct here. I will check later. So we do Friedel-Crafts reaction. We have benzene, we have alkyl halide, we have catalyst, aluminum chloride to do the Friedel-Crafts reaction to introduce methyl group. Good news, the methyl group does not have carbon cations rearrangement because only one carbon here. So the next step is to introduce the nitro group. So again, this methyl group is a weak electron donating group to the benzene ring. So it is a meta and a para director. So when we do the nitration reaction, the nitro group either introduced to the alpha position here or the para position here. So at least this is one of the product from this reaction. The next step is the oxidation reaction of this methyl group. So basically we oxidize this methyl group CH3 here to COOH acid group again. The name here is para-nitrobenzoic acid. Para means, you know, this is a benzoic acid. It's a benzene plus acid here. Again, this is the structure here is not correct. It should be COOH. This is nitro group is at the para position. This is relative to this acid COOH. This is para position. So we call this para or P nitrobenzoic acid. I will change the structure here. So this is the whole process to make this target molecule. Basically, this should be the P nitrobenzoic acid. All right, that's all I want to share with you for chapter 16. We finished chapter 16 today, and we are going to start chapter 23 next time.